Hello everyone, welcome to NPTEL online certification course on fundamentals of food process engineering. We will continue with the topic of heat exchanger today. So, in the last class we have discussed a few things, the definition, types of heat exchanger, and today we will start analysis of heat exchanger. Okay. So, as you know that heat exchangers are very important equipment, and that is most commonly used in many food processing application. So, we need to know that what are the basic parameters or important parameter based on what thing we can design a heat exchanger. Okay. What are the important parameters? So, today we will learn those things. So, analysis of heat exchanger, if we want to do, the first thing is we need to know that the overall heat transfer coefficient, this is very important factor. Another important is the surface area, then inlet and outlet temperature T1 and T2 okay, of the two fluid, right. So, if we want to analyze a heat exchanger, the main important parameters are what are the two fluids and what are the inlet and exit temperature that we want. That means, if we want to use the liquid, the cold fluid, which is our interest. So, how far we need to increase the temperature from TC1 to TC2, and for that what is the amount of hot water or any hot fluid is needed, what will be the temperature. Then we need to know that the surface area, okay, the surface area available for heat transfer. This is very important, because if surface area changes, then obviously the rate of heat transfer changes, because normally the rate of heat transfer is expressed as Q equal to U A delta T, where U is the overall heat transfer coefficient, A is the area, and if A changes, so in that case, because U is constant, so then delta T will also vary, right. So, that is why this is very important parameter. So, heat exchange here happens via the heat exchange surface, and when we try to analyze this thing, the first thing we need to know is we need to balance, we need to see the overall energy balance or heat balance between the two fluid. Okay. So, now considering the figure that we have seen just now, that the hot fluid is entering and the cold fluid is also entering, and those two have a similar direction. So, they are in the parallel flow direction. So, if we want to analyze now the heat given up by the hot fluid, okay. So, that will be Q into mH dot, that is the mass flow rate of the hot fluid, Cph specific heat of the hot fluid, and Th1 minus Th2. Th1 is greater than Th2. So, heat given by this will be this quantity, okay. Whereas, the similar amount of heat will be picked up by the cold fluid if we assume that there is no heat loss, right. So, the heat gain by the cold fluid will be mc dot, that is the flow rate of this, into Cpc, the specific heat, into Tc2 minus Tc1. Okay. So, because it is increasing the temperature from Tc1 low temperature to the high temperature Tc2, right. So, total heat transfer rate in the heat exchanger is equal to U A theta m. So, this total heat transfer is U A theta m, because this whatever heat it is given, the hot fluid is giving and the cold fluid is taking, that is happening across a surface area, okay, surface area A, and theta m, this is actually signifying the difference between the hot and cold fluid. So, theta m we can write in this way, T h minus T c, right. So, m dot is the mass flow rate, m h dot indicates for the hot fluid mass flow rate, and m c dot is the mass flow rate of the cold fluid. C p again the specific heat, as I mentioned, for the hot and cold fluid. Delta T is the temperature rise or drop across the heat exchanger. So, theta m can be termed as theta m, this can be termed as delta T, right. So, any terminology you can use, either delta T or theta m, both are same. Okay. So, now theta m is log mean temperature difference. Okay. So, why we are telling it as log mean temperature difference? I mean delta T, which is the gradient, okay, delta T which is the gradient between the two fluid. Okay. So, this is actually the temperature rise or drop across the heat exchanger. Okay. So, let us say if since these two are parallel flow. So, this way the heat flow is going, this is the T h 1, T h 2, T c 2, T c 1, right. So, delta T, this difference can be calculated in many ways, right. So, one such way is by calculating the log mean temperature difference, and we will see that why log mean temperature difference is so important. Okay. So, we can write this Q, that is equal to U A delta T, signifying that delta T is the pressure drop, and we also can signify it as U A delta T m, where theta m is log mean temperature difference between these two fluid stream. So, what is log mean temperature difference, right? So, it is defined as the temperature difference which, if constant, would give the same rate of heat transfer that actually occurs under variable condition of heat transfer. So, let us check this by calculating the value of LMTD. So, most of the cases, in case of heat exchanger, we consider the steady flow, because in heat exchanger it normally allows to run for a longer time. Okay. So, generally the heat transfer in case of heat exchanger follows the steady state. So, we take certain assumption here to calculate the log mean temperature difference. First is the steady flow will be occurring in the heat exchanger, steady flow of both the stream. Then the next is specific heat, mass flow, and overall heat transfer coefficient is constant. Okay. So, we will discuss the overall heat transfer coefficient concept in detail, and maybe some of you have learned this in your heat transfer course. However, we will discuss that. For this moment you understand that this is the overall heat transfer coefficient. Okay. Specific heat and mass flow will also be constant. Then heat exchanger is preferably insulated, that means we consider that there is no heat loss to the ambience. Whatever heat the cold fluid is getting, that is coming directly from the hot fluid. Okay. No phase change of the fluid during heat transfer. So, the heat that is transferring is causing sensible change of both the fluid, no latent heat or no phase change is involved. And the last is heat conduction in axial direction is negligible. Okay. However, one more assumption you might take, that no change in the potential and kinetic energy will be there. So, with this assumption we will see that logarithmic temperature difference for parallel flow, right. So, parallel flow, we know the configuration, the hot fluid and the cold fluid are moving in a similar direction, and temperature profile across the area, if you draw or if you plot it, you are getting this kind of a plot, which is the difference between these two, that is delta t, or if you take theta. So, that theta is gradually decreasing, theta 1 T h 1 minus T c 1 and theta 2 is T h 2 minus T c 2. So, if we consider an elementary area dA, okay, here in the heat exchanger, the rate of flow through this elementary area will be dq, let us say. So, that is u dA into difference between two streams Th minus Tc, or u into dA into delta T. As of now we are not considering that this is LMTD, just we are taking that delta T is the temperature gradient between hot and cold stream. So, the hot fluid is cooled. Okay. So, the dTH, that means the lowering of the temperature is happened. So, we are considering this as negative, whereas dTc, if you consider, that is the change, the differential change in the cold stream in the temperature, that is positive, right. So, dQ will be equal to minus mH dot, that is mass flow rate, into Cph specific heat into dTH. We are putting minus sign because of that, and this Q will be mc dot Cpc into dTc. So, there is a positive change in the direction of the area. So, that is UA delta T. So, then we can write dTH is equal to minus dQ by mH dot Cph, or dQ by Ch, where Ch is the heat capacity or water equivalent of hot fluid, and dTc can be written as dQ by mc dot Cpc or dQ by Cc, where Cc is the heat capacity or water equivalent of the cold fluid. So, heat capacity of the cold fluid. Okay. Now, subtracting these two, dTH minus dTc, because this is what, this is actually the gradient of temperature between those two streams across the area dA. So, dTH minus dTc will be, we can take this minus common. So, 1 by Ch plus 1 by Cc. So, minus dQ from here and here we have taken common. So, 1 by Ch plus 1 by Cc remains. Okay. Then what we can write is d theta, okay, that is nothing but dTH minus dTc. Okay. So, d theta, that is equal to minus dQ 1 by Ch plus 1 by Cc. Okay. So, again d theta equal to minus u, because this q can be written as u dA into theta, the temperature difference. So, that is Th minus Tc, okay, delta T. If we consider that dQ, this is equal to u dA delta T. So, we can write delta T as Th minus Tc into 1 by Ch plus 1 by Cc. So, this Th minus Tc is termed as theta, okay, and theta. So, u dA theta into 1 by Ch plus 1 by Cc. Now, we need to integrate this, because d theta is the differential change in the temperature difference of the two sides or two fluids from 1 to 2 section. Okay. So, A equal to 0 to A equal to A, if we integrate initially A equal to 0 to A equal to A, that means the total area. So, theta will vary from theta 1 to theta 2. Theta 1 is the difference of those two stream in the inlet condition, and theta 2 is the difference of those two stream in the exit condition. So, integrating this d theta by theta from 1 to 2, that is equal to minus u a equal to 0 to a equal to a d a 1 by C h plus 1 by C c, and we are finally getting this equation ln theta 2 by theta 1, that is equal to minus u d a 1 by C h plus 1 by C c. Okay. So, heat capacity of the hot fluid plus 1 by heat capacity of the cold fluid. Now, the heat Q, that is the total heat Q, has been given by the hot fluid, that is C h into T h 1 minus T h 2. Okay. So, if we want to write that heat balance, so we are getting this one, that is equal to C c into T c 2 minus T c 1, because H 1 to H 2 the change has happened, the heat it has given, that is been taken by the cold fluid. So, T c 2 minus T c 1. So, from here we can write 1 by C h, okay, 1 by C h, that is equal to T h 1 minus T h 2 by Q, and 1 by C c is T c 2 minus T c 1 by Q. Now, this one and this one we are going to put in this equation. So, substituting the values of 1 by C h and 1 by C h, okay, and 1 by C c. So, we are getting that T h 1 minus T h 2, okay, plus T c 2 minus T c 1, and if I take this minus inside, I can write T h 2 minus T c 2 minus T h 1 minus T c 1, right. So, here T h 2 minus T c 2, this is equal to theta 2, and T h 1 minus T c 1, this is equal to theta 1. The temperature difference of the both fluid stream in the inlet and exit section. So, I can write U A by Q into theta 2 minus theta 1, or Q will be equal to U A theta 2 minus theta 1 divided by ln theta 2 by theta 1. So, that is again termed as U A theta m, right. So, theta m is this value theta 2 minus theta 1 divided by ln of theta 2 by theta 1. So, this is called log mean temperature difference, LMTD. So, that is why we can calculate that why this log mean temperature difference is very important, and normally we use this one. Now, this we have solved for parallel flow. The similar case we can solve for counter flow as well. So, in the counter flow what happened, that the two fluid streams are moving in opposite direction, and the hot fluid and the cold fluid temperature distribution across the area will look like this way, where theta 1 is T h 1 minus T c 2 and theta 2 is T h 2 minus T c 1, and these two temperature difference theta 2 and theta 1 are may be almost constant, or there is not much variation between them. So, theta, that means at any instant if the difference between these two streams we consider, we will term this as theta, and here also if we move on this direction, I mean positive area direction. So, hot fluid is reducing temperature. So, dTh is again this is negative, and dA, while across the area if we go, here also it is negative because the flow direction is now reverse, right. So, then we can write here Q is equal to minus mH dot, that is mass flow rate of the hot fluid, Cph specific heat dTH, the temperature difference across the small area dA, that is equal to minus mc dot Cpc into dTc, because again dTc also reducing because the flow direction of the cold fluid is reversed now, right, and this is equal to U dA delta T. Okay. So, the similar approach that we have taken for the earlier section we will apply here. So, what we can do is again we will write dTH, that is dQ by mH Cph. So, that is dQ by Ch, and dTc will be equal to dQ by Cc. Now, dTH minus dTc, that is the temperature difference across the area dA, that is dQ will take common into 1 by Ch minus 1 by Cc. Okay. And again we can term this as d theta, right. So, d theta equal to dQ into 1 by Ch minus 1 by Cc, and dQ will be written as U into dA differential area into Th minus Tc, the temperature difference between two stream in the area dA, right. Now, from this what we can do, Th minus Tc will term as theta, we will take d theta by theta and then we will integrate this and we get this term, that is ln theta 2 by theta 1 in the left side, and in the right side what we can do, we can again put the values of 1 by Ch and 1 by Cc as we did in the earlier case. Now, here what we can do is Ch, the hot fluid, it is reducing Ch into Th1 minus Th2, and the cold fluid, that is going from Tc1 minus Tc2, the direction is reversed now. Okay. Tc1, if we move in this direction, this is actually going from inside to outside, but since there is a opposite direction, we have a minus, and that minus we have introduced here. Okay. So, we can write this now as C 1 by Ch, 1 by Ch will be 1 by Ch will be equal to Th2 minus Th1 by Q, and 1 by Cc will be Tc1, 1 by Cc will be Tc1 minus Tc2 by Q. Okay. So, we will put it here Th2 minus Th1 by Q minus Tc1 minus Tc2 by Q. Okay. So, eventually we will get this expression that ln theta 2 by theta 1 equal to U A by Q theta 2 minus theta 1. So, Q will be U A theta 2 minus theta 1 by ln of theta 2 by theta 1. So, Q is equal to U A theta m, or log mean temperature difference is theta m. However, here as it is mentioned that theta 1 will be difference of Th1 and Tc2, not Th1 and Tc1. Okay, and theta 2 will be difference between Th2 and Tc1, because it is a counter flow problem. Now, there are a few cases where theta 1 equal to theta 2. Okay. So, theta, so it is remain constant, it is theta which is from the inlet to the exit side remain constant. So, the temperature difference between those two fluids are constant. So, in that case the equation will be simply Q equal to U A theta. Okay. And log mean temperature difference for a counter flow heat exchanger is always greater than parallel flow heat exchanger. Okay, log mean temperature difference for counter flow is always greater than the parallel flow heat exchanger. But when the temperature difference between them is small, okay, in that case the arithmetic mean temperature is used. That means, if theta 1, so we will better write it as when the temperature difference between theta 1 and theta 2 is small. Okay. So, in that case arithmetic mean of the temperature is being used. So, generally LMTD for counter flow heat exchanger is greater. That means, if log mean temperature difference we are getting higher, so area can be reduced, right. So, therefore, for the counter flow we can require less area compared to the parallel flow, okay, for the same amount of I mean the same temperature distribution if we have. Okay. So, we will stop here and we will continue in the next class. Thank you.